Welcome to Josh Watts, Director of the National Battery Testing Centre and Energy Storage Research Group at QUT. Josh has over 14 years of research and development experience, primarily focused in the fields of battery energy storage and renewable energy generation. So looking forward to hearing from Josh. Thanks, mate.
Hey everyone, how you going? Thanks for having me, and thanks to Masters Electricians for inviting me out to have a chat to you all about everything batteries. I'm a research scientist, material scientist by trade, but I've worked in the energy storage industry for about 20 years. So have done a lot of materials pilot scale work, but I've also done a lot of systems development and battery testing and deployment as well. So I'll get into it in more detail, but a lot of what we do is testing and prove out of different battery technologies, as diverse a range as possible, to mainly try and support adoption of systems locally, to give consumers confidence in technology, especially new and emerging technologies, to support the net zero transition. But we also do a lot of research and development at fundamental scale as well to actually make the batteries themselves. So similar to the previous talk, I'll just quickly highlight, I guess, the proposed market opportunities, especially for batteries. It's a huge growth industry, and there's a massive amount of value add for Australia to be able to participate in here. At the moment, we really do just sort of dig and ship a lot of the raw materials that we need for the to make batteries, and we need to change that for a lot of different reasons. One of the main ones being our own energy security, to make sure that we can actually have the technology available locally and made locally. So our research group and what we do, we participate in the whole value chain. We do a lot of work in taking the raw chemicals and minerals that local miners are making and supporting them to find ways to refine out to the high purity chemicals you need to make the different battery types. But then we also do the value add part at pilot scale as well. And then we actually make batteries, lithium batteries, flow batteries, and then we do a lot of testing and support the deployment of those systems nationally as well. And there's a throughout this whole value chain, even back into recycling and reuse of batteries, that there's the opportunity is massive. Like it's estimated in a report last year from Accenture about $16.9 billion in value add for Australia. We have over 50% of the world's minerals that you need to make batteries. So we've got over 50% of the lithium, over 50% of the cobalt. We just have so much of those raw materials here that we can actually literally become a bit of a superpower in space if we actually focus in and start targeting strategic areas to value add and move through to the manufacturing. We haven't started really manufacturing batteries, especially lithium, yet because we don't have the supply chain in place to be able to actually make them at scale, and we don't really have the offtake yet either. But those things are starting to change, and that's a big part of what we do, is supporting companies and supporting industry to translate new ideas out of university and other academic places to commercialize technology to move towards manufacturing of the systems. So the QT Advanced Battery Facility, like I said, we have a full vertically integrated pilot scale facility where we can do all of the materials research to actually the materials that goes into making the batteries. That includes lithium batteries, flow batteries, also moving into sodium ion batteries as well, and also moving into molten metal liquid batteries as well. And then we can do all of the integration of those materials into the cells, so we can actually make the cells. We're the only place in Australia currently that can make cylindrical cells that you use in lots of different applications, including EVs and other things. And we do the pouch cells as well. So we can take that, take the materials, integrate them into the cells, and then do the prove out and testing of the cells as well. And that part is really critical for enabling and growing battery industries locally, because without having that ability to support industry with those resources and access to the capital intensive equipment you need to do the testing, it's really difficult for the industry to grow. And it's that third party testing and validation side of things, all the way from the materials all the way through to the cells and systems, is really critical to supporting and growing the industry. If you look overseas in Germany and Europe, States, Japan, wherever, where they have a strong battery industry, these support hubs are central to it. They're absolutely necessary part of the industry, and that's not even talking about certification and standards as well. You need to have that parallel capability to enable the adoption and also for safety as well. And then we also do a lot of training. So I should mention on the previous slide, there's a huge job opportunity here, but we don't have a lot of the skilled workers, to fill these jobs. And so, especially when you get into the battery side of things, there's very highly skilled workforce needed, like postdoc qualified type things to be able to do the materials level stuff. But then even as you go through to the manufacturing and doing that value add piece, there's we currently have a massive skill shortage in the space. So we're doing our best to support the universities, work with industry, try and find where the skill gap is and develop training programs. And I'll talk a bit more about that later as well. Just a quick snapshot of a few of the major projects that we currently manage at QUT. Again, it's looking across the whole value chain. So we work with the front-end materials side. So if you just talk to lithium batteries for EV applications, for instance, the main inputs for that are nickel, manganese, cobalt sulfates, and lithium hydroxide. Currently in Australia, we have all those raw materials, but we don't necessarily refine to the high-grade materials that you need to manufacture the batteries yet. But a lot of the miners and / refiners are starting to do that, starting to refine the nickel to nickel sulfate and cobalt to cobalt sulfate, so they can participate in the value chain. And a big part of what we do is we can take those raw feedstocks and we can actually manufacture the battery materials at pilot scale, and then we can put those into cells, test the materials. We can actually do the pilot scale processing as well to actually increase the cell capacity and go up and support the prove out and commercialization of the larger cell formats. And that's really critical part of the process as well. As I said, we make the cells at commercial grade as well, all the way up to cylindrical cells, and then we can actually take the cells, put them into the modules, make the battery packs, test the BMSs. We even do have our own internal power conversion research group where we're developing brand new DC converter technology to support integration of batteries with renewable systems. So there's a big opportunity to move towards local DC connectivity, so going to AC and back to DC again. It's been limited by the componentry that you can put into DC converters to be able to have the current handling and the efficiency, but that's changing. And so there's the ability now to develop new DC converter topologies, for instance, to be able to do that job a lot better. So we have a research group working on that stuff as well. And we can go through, put all the bits together and actually build the systems or test other people's systems. So the National Battery Testing Centre project, for instance, is working towards building some of that certification capability locally as well, supporting the compliance with the standards, but also, supporting industry to innovate and put new systems together, look at different ways we can support the batteries for renewable integration is a big driver. So I mentioned we have the pilot scale processing capability for lithium batteries, and we're also developing it for flow batteries. And this system here, this feedback mechanism where you can take the materials, put them into small cells first, which are the coin cells is what we call them, is what we use to do the initial testing of the materials, whether it's the anode material, the cathode material, which are generally powdered materials, or the electrolyte or the separator, the different bits that go into the battery. We can go through and build those materials from scratch, and then we can actually put them into the cells, test them, work with our industry partners to prove it out and scale it up. And the nature of the way that you go through the commercialization process and scaling process of lithium batteries in particular, but it works for most, it's true for most battery systems. There's a really long, arduous development cycle, just because of the nature of, as you go up and scale the battery capacity is getting bigger, and to prove out the system and the cells themselves and make sure there's no issues, you've got to test them for long periods of time and you've got to test them in high volumes. So the nature of the battery development cycle, it just takes a long time. Having all the capital equipment that you need to be able to do this process, to be able to do the testing, scale the cells, is really expensive equipment. So a lot of startups and SMEs who are moving into this area can't afford to buy that and source in that equipment. So we provide that service, working with industry in parallel, subsidised by a lot of government grants, to be able to support industry to innovate and move downstream towards manufacturing. And that's a big goal of what we're doing and trying to support and grow industry is value add to Australian minerals to move towards developing the supply chain that we need to actually manufacture the batteries. We make the batteries at sort of pilot scale, so we can make the cylindrical cells, pouch cells, coin cells, but we don't sell them. It's mainly for supporting industry to do that prototyping and scaling exercise. You'd probably notice nobody makes cells yet in Australia. None of the big guys, Panasonic, they haven't set up factories here, and that's because the supply chain's not there and the offtake on the other side's not there. But that will change for sure, and as we build the supply chain, these kinds of services become more and more critical. So working with federal government, state government, we're currently working through expanding capabilities to support industry and build that out. And that includes other technologies as well, like flow batteries. As you go up into the larger technologies, the larger format, the bigger systems, there's also safety testing you've got to do. And the nature of lithium batteries, they can catch fire. If they're looked after, though, if you're using high quality cells, high quality systems, there's so many different sub levels of safety, all the way from the cell level, all the way through to the pack and the battery management system that are put in place to make sure that they can't go bad. I'll talk a little bit more about some safety stuff later, but as you go up into that large scale, you've got to have very bespoke test fixtures to make sure that your testing is done safely and you're protecting your people and the infrastructure. We haven't had a battery fire yet at our facility, touch wood. It's not wood. But every other national testing facility that I talked to has had multiple. And I was just over in Europe a couple of months ago and having a look at one of these chambers, much bigger than the one you see up here, that's recently had an event, and it's pretty scary. So especially as you go up into the EV packs and bigger packs, you really need to have very expensive bespoke infrastructure to be able to test them safely. I'll talk about it a bit more, but we're currently working with Queensland Fire Emergency Services to develop destructive testing capability so we can test the systems safely, put them into abuse conditions, and look at how they fail to help inform like the fire engineering and standards developed around the systems. So everything before here, up to this space here, the top end, up to the pack testing, we can do up to about 20 kilowatts internal to the building. But as you go up into larger systems, we tend to move outside. And so we have developed a battery testing microgrid at our pilot plant precinct in Brisbane, which is where our facility is, where we can test the larger systems as well. So this has been a bit of a slog, but we're nearly there on having this fully commissioned, and it's been set up in a way that we can sort of use a large lithium battery on the front end of the grid and then test lots of different smaller batteries behind that. And at the moment we've been testing, I'll talk a bit, a large iron flow battery, but the grid is in really high demand at the moment from lots of local systems manufacturers and new technology importers where they want to drop a new system, a new technology down, do the prove out, do the certification, or try and comply with what standards we do have to get the systems ready for deployment. And it's really it's probably an understated importance of this is people won't buy the technology, they won't deploy it, they won't even interact with it until they've seen one running and working. And that's a big part of what we're trying to do is where we can import non-lithium systems. We still do a lot of lithium work, but looking at other things like molten metal batteries, flow batteries, and other emerging energy storage technologies, so we can test them, work out where they best fit inside the energy infrastructure. All these different batteries have different use cases where they perform the best. So lithium is really good for short duration. Whereas the long duration storage, you really need, flow batteries, liquid metal batteries are better suited for those applications. And part of what we're doing with this, the grid development is to be able to have lots of different kinds of battery systems on a common microgrid, so we can look at hybriding of the systems and pairing them up and really playing to where the systems operate the best. Lithium batteries, for instance, don't like being hot and they're not very good for long duration, and they're expensive. So they might be good for just to very pulse initial fast response, but then you can potentially transition to longer duration storage behind that. And then you're not hitting the lithium battery as much, and you're making use of the long duration energy storage that way. We're looking to have a few other energy generation bits and pieces on the grid too, but it's mainly looking to test the energy storage systems themselves. So this is ESI's energy warehouse, so 75 kilowatt, 400 kilowatt hour iron flow battery. So flow batteries are potentially quite a good solution for long duration energy storage applications, because the power and the capacity are separated, so you can actually just increase the volume of your tank to increase the capacity. So unlike a lithium battery or other intercalation type energy storage systems, with a flow battery you're storing the energy inside the liquid itself. So if you need a longer duration storage battery, more storage capacity, you can just increase the volume of the tank, not the whole system. Whereas lithium batteries and other technologies, if you want more capacity, you have to multiply the whole system, which is not very cost effective. So this is, I guess, a newish technology coming through. Vanadium flow batteries are sort of where it started in the late 80s, early 90s. But people have been looking for different chemicals that they can use to store the energy in the liquid medium, and iron flow is where they've landed on one. So this is a company in the States manufacture these batteries, and ESI is a local company I was looking to is importing the systems and then also trying to onshore the manufacturing of the systems. And again, it's similar to a lithium battery scenario where we don't make any of the bits locally that go into making the system. So to action onshoring manufacturing of these systems, we need to build the supply chain as well. And so there's lots of different bits that go into a flow battery. They're actually quite similar to lithium batteries. So separator membranes, for instance, are just a plastic membrane made out of different materials depending on the battery. We don't make that here in Australia either. So there's opportunities to look into R&D and looking to move downstream into manufacturing that, so we can onshore manufacturing of these systems. So we've had one of these running since January this year. This was sort of a 2-year procurement and installation process. It took a lot of time to work through all the hurdles around, procurement, transport, installation. But as part of that process, we've got a best practice document we're working through now, so we can support the deployment of integration of these nationally. As I said, this is a 75 kilowatt, 400 kilowatt hour system. And since January, we've gone through with the partner ESI, and done a fair bit of testing to prove out the system. And a lot of that's been working towards getting it compliant to Australian standards, but also looking at ongoing service and maintenance for the system. So flow batteries, unlike lithium batteries, you've got to treat them like a piece of plant. They have lots of pumps, they've got stored liquid in flowing pipes, large tanks, scrubbers, things like that. So, they require ongoing service and maintenance to keep the systems up and running. And that's a big part of what we're doing, as well as looking at the lifetime cost of storage for these things, looking at what the ongoing service and maintenance of the systems is, what the costs are, looking at the uptime of the systems, which is a really big one for end users, to build confidence in the technology that they're fit for purpose. They're working on this system since January, and the manufacturer as well in the States. We've been able to make a lot of improvements to the system, bring it up to Australian standards, and the testing that we've done here has unlocked further supply of this in Australia. And we'll probably say recently there's an announcement in Queensland for a lot more of these systems to come in to support one of the government-owned energy corporations in their clean energy transition efforts. So yeah, this is one system that potentially has a great opportunity for Queensland. It's also the iron electrolyte that it uses is non-toxic, whereas vanadium, it can be quite toxic, or it is quite toxic. So this has another advantage where it's a little bit more environmentally benign and friendly. And we've got a lot of iron resources in Queensland and Australia as well. And there's already efforts to value add to our iron resources to make the electrolyte and even supply that electrolyte to the States for these systems as well. So as part of the microgrid, we're now just finishing off the installation of a 400 kilowatt hour lithium battery from Red Earth, one of our industry partners. That's LFP chemistry cells, and this is a grid forming battery. So in the first instance, the grid is off grid, and we're looking to connect it to the 100 kilowatts of solar we've got on the roof to support renewable testing of the system. So basically, this becomes the power module of the grid coupled with the solar, and then we can keep this battery topped up, and it can discharge into the other batteries under test. And when those batteries are discharging, they discharge back into this battery on a common AC bus. So that allows us to test sort of behind the battery and test systems that don't have compliance yet. We can also look at power conversion systems integration as well, and testing of a wide range of different battery systems to support bringing them up to Australian standards, but also doing that R&D piece around the systems. So yeah, this is just being commissioned now with the iron flow battery and a few other battery systems. Switchboard arriving next week, which is exciting. And yeah, this is a locally manufactured system. The cells, obviously, no one makes cells yet in Australia. There's a company called Feline in the Gold Coast that makes prismatic cells, lithium cells for defence purposes. But that's it in Australia. So anyone who's using lithium cells, they're importing cells. So this uses high quality CATL cells, and SIL is the partner that does the container, as well as the power conversion system. And so this is a grid forming battery. So it's like a Red Earth Kookaburra system, I think. So we go up to 250 kilowatts, and we're running it at a 125 kilowatt configuration to do grid testing. So this is another type of energy storage for long duration that I guess not many people are really aware of yet, but it's become awareness is being raised just because of how useful they are. If you want a battery system that just sort of works off the shelves, commercially proven out, you've only really got two choices. One's lithium, and then the other's this, which is a NAS battery, so liquid metal sodium sulfur. So this technology was commercialized 20 years ago by BASF and their subsidiary NGK, and they're manufactured out of Japan. So we've just deployed one of these systems. Actually, this is just some pictures of the systems installed globally. So just highlights that the system has been around for a long time and has high international utilization, especially in Japan, Korea, and Europe, for lots of different energy storage applications. These systems are, I guess, really strong counterpart with lithium because they do the long duration side. So they're a minimum 6-hour duration battery. They actually can't do less. So the current market demand for energy storage is sort of sitting more around the 4 hours. But these are, as I was saying, these are going to be very high utilization for renewables integration going forward as we move to longer duration storage requirements for renewable energy integration and winding down carbon intensive generators. So we've just installed this in January as well, actually with IGO over in WA on their Nickel Nova mine site. So it's two 20-foot containers. One 20-foot container is the battery, and the other houses all the power conversion systems. The beauty of this battery is it doesn't need any HVAC, doesn't need any cooling, whereas lithium batteries, they need to be kept cool. They only operate well between 15 and 35, 40 degrees. Anything outside of that, the battery's either starting to die at high temperature or you're losing efficiency at low temperature. Whereas this battery runs at 300 degrees. It's a molten metal battery. So when you ship the battery, it's actually shipped in a fully charged state with solid metal sodium, solid metal sulfur on either side of the battery. And then when you turn it on, it heats them up, they liquefy and they combine and release energy. And it's that simple for this type of battery. So, like I said, this has been commercialized off the shelf for the last 20 years. And the price point of this is actually really, really close to lithium. So once you take into account all of the benefits you get from it, including the lower cost of maintenance of the system over time. So this system at IGO's mine site's been running since January, and I think I have some. So this is a picture of the battery installed at Nova's mine site. So that's the battery at the front side, and behind that is the 20-foot PCS. The solar on the roof is just a bit of a token effort, to be honest. It's actually connected to their main grid, their mine site grid, which just had, I think, 17 megawatt of solar installed. So this battery is, I guess, what we call a demonstrator. We're just running the battery full charge, discharge, one cycle a day, mainly just to look at uptime and do any of the prove-out work that we need for the connection to the PCS system. And since January, this thing's been running just non-stop without a hitch, which is really impressive for something that's out in the middle of WA out in the heat, dusty area. They just work. And you can see this bit at the end, that was just a firmware upgrade. So part of what we were doing, working with InDrive Check, the PCS manufacturer, they had to come in and do a firmware upgrade, so the battery was down for about a week there. But yeah, it's just a technology that off the shelf really works and has a really good potential utilization for long duration storage applications. So we've got plans to deploy a few more of these. So there'll be one of these in Queensland soon. You'll probably hear an announcement around that through our research group and the state government, Queensland State Government. And then there's plans to do larger arrays of these systems, so then move into the 8, 16, up to 5 megawatt storage capacity, power to prove out the systems in larger configurations. We're also very active in the lithium battery safety space, and also working towards supporting standards development. So what we do with that fundamental vertically integrated R&D piece that we do from start to finish for the lithium batteries, we're doing a lot of innovation there at the materials level to actually try and increase the safety of lithium batteries as well. So there's lots of things you can do at the materials level, at the cell design level, to increase the safety of these systems, and that's really where the industry's heading for lithium batteries, is increased safety, especially for large-scale systems. There's a real need to improve the safety of the system. So there's things you can do, like put coatings on the separators with nanomaterials and ceramics to increase the resistance to high temperatures, to stop the thermal runaway mechanism from taking place, which we're working with people like Lava Blue and Alpha HPA to do some of that work. But also, working with the working groups, the standards working groups, to try and push things along. And we do a lot of testing. That's sort of our bread and butter for the different systems. So we can use those data sets, use that experience to feed into the standards committees to try and support uplift and actually push things towards where they need to go. Like I said, there's potentially high utilisation in Australia for flow batteries, but we don't have any real standard that talks to what's needed to install a flow battery safely. And that's something that we need to look at doing pretty soon. So we work very closely with local fire emergency service in Queensland, but we also work with the National Fire Emergency Services to support training their people as well around the hazards around lithium batteries. We work with the fireys a lot, and their panic stations about some of this lithium battery stuff in particular, because they don't know what to do to a degree, and it's a problem globally. It's not really understood what the best practice is to fight lithium battery fires, because they are a very unique type of fire. They produce their own fuel, they produce their own oxygen, so even if you submerge them or put them under inert conditions, they're just going to continue to catch fire. So they're very hard to put out. They burn at very high temperatures. The fire emergencies PPE melts at the temperatures that battery fires go off at. So there's concerns, especially around EVs and tunnel systems as well. What happens if an EV goes up in a tunnel? There's not really best practice to lean on at the moment as to what you do in those situations. So working with the Queensland Government and a few industry partners, we're developing the Queensland Energy Storage Technology Hub, which is Quest Hub, and that's doing a lot of things, adding to the value adding to local minerals to develop those components that we need to manufacture battery systems, but also moving into a lot of flow battery R&D to support scaling up of those types of initiatives. A big part of the focus on this is working with QFES and the Queensland State Government to develop destructive testing facilities at their Life Fire campus. So it's not really well known, but QFES has in Brisbane the White Island Life Fire campus, which is a really unique facility. I think there's only about 3 or 4 of them globally that do what they do, where they have like old airplanes, old trains, old buses plumbed in with gas, where they can bring in fireys, cadets, and actually put out real fires in real situations and expose them to that to train them up. And so we are with Queensland State Government and QFES putting together some destructive testing capability there for batteries, where we can actually demonstrate what happens when batteries go bad, to support training the fireys up on emergency response and developing their emergency response procedures in parallel as well. But that capability to be able to test batteries to destruction is really important for integration and adoption as well. Different batteries lithium batteries or different chemistries can fail in different ways, depending on the battery management system, depending on the cell chemistry. So, and once you put all these things together into a system, they all have their own unique failure mechanisms and situations. So it's really, especially for the integration of these systems in safe manner, it's really important to be able to test the batteries in abuse conditions to try and help inform how best to integrate the batteries. And it's a bit of a how much do you care at the moment situation as far as that goes. So, as in there's a sweet spot for cost for people there, that they don't want to put too much money into it, but how much is good enough to make the battery safe. So that capability is really, really useful for industry as well. I don't know how long I've been talking for, but I'll probably call it there. If you have any questions or anything about batteries, please feel to reach out, and thanks for having me.